in the table of the contents of this class is about model order reduction using moment matching techniques. Last time, if you remember, we discussed some very interesting numerical issues and numerical methods regarding the solutions, solving linear systems of equations, okay? And we remembered, and not only that, but especially problems related to such say, multitudes of or such classes of methods, problems like such as eigenvalue decomposition and SVD decomposition, okay? And we talked about some very interesting procedures, the Arnoldi method and the Lanczos method, okay, about the specific computations of matrices where the eigenvalues are approximated, or the eigenvalues of those matrices approximate the set of eigenvalues of the original matrices we would like to compute, okay? And these methods are very interesting because they employ specific projections. Essentially, if you want to easily compute your eigenvalues, you can project your matrix onto a specific space with some projection, okay? So essentially what I'm saying is I want to talk about the spectrum of matrix A, but instead of computing the spectrum of matrix A, which is large, okay? Usually, because this is regarding large matrix computations, okay? This is not about simple matrices. If you have the matrix 0, 1, 5, 6, you can analytically compute the eigenvalues and the singular values. However, you're not able to compute the eigenvalues or the singular values for matrices, say 10,000 size, or 100,000 size, or maybe a million size, okay? That's not possible. So what you usually do, you project. You consider a projection V, you consider a matrix W such that W transpose V is the identity. Essentially, V is a tall matrix and W transposed, okay? So this is V, this is W transposed. W transposed is a wide matrix. Multiplying them, you get a square, small size matrix. So if this is nu, this is ni, and this is n, this is ni, this resulting matrix is ni by ni. And usually ni is much smaller than n. Okay? So you project this matrix. So what you do, you compute the invariant subspace AV, and then you take W transposed, and then you get a smaller matrix A hat. And it's easier to compute the spectrum of the matrix A hat rather than compute the spectrum of A. Of course, the spectrum of A hat, okay, is not the spectrum of A analytically. Okay, it's only fair. But the spectrum of the matrix A, okay, approximates a part of the spectrum of this matrix A. So it's sort of included approximately in the spectrum of the matrix A. Okay, so why not use this fortunate idea for model order reduction of dynamical systems? So if you have the dynamical system X dot is AX plus BU, we have talked about this before, and we have the matrix and the output Y is CX. So you have this system, let's call it sigma, with input U, state X, and output Y. Okay, and usually with X in Rn and N very large, or N, let's put it like this, N big. Okay, from big data. Right? So that means that A, B, C matrices are huge matrices. Okay? All right? How can we find, so this is the model reduction problem. I want to find sigma hat with psi is F psi plus GU, or let's just not call it sigma hat, let's call it sigma G. And you'll see why later on. Let's call it sigma G, somewhat this indicates that you parameterize this system in this matrix G. And with the output, it's not the same output. So this is, say the output eta equals h psi. Okay, this is psi dot. Okay, with the state psi in the space R ni much smaller than n. This is what I'm interested in. Okay, mathematically, it's interesting to compute sigma equal n and sigma larger than n. I've got papers where I study these cases as well, because mathematically it makes sense. And sometimes there is areas where people, to be able to compute something, include their state space system into or embed their state space system into an augmented system. Okay, right. So this time, and I'm going to apply to do this, doing the following thing. I'm saying that between x and psi, there is a relation. This is the relation. X equal V psi. I remind you that V is R n times ni. Okay, R times ni. So V is like this. Okay, fine. Hence, I just need the other matrix W transposed, and you have W transpose psi is X. Okay, so such that W transposed V is the identity. If you can do that, then you can easily pick. Okay, we know that I've shown you 100 times. Yeah, V psi dot is A V psi. Yes, plus BU. This is the original system, and then you multiply this by W transposed, and then you get the psi dot is W transposed AV psi plus W transposed BU, and Y. Well, this is not actually Y. This is CV psi. Well, it's sort of a Y, but it's not necessarily the same. Okay, all right. And this is your new system. This is F. This is G. This is H. Okay, this is your new system. Okay. Now the question is Y. Let's put it eta. However, let's make it eta. Eta. Okay. Is eta close to Y? What's the criterion? Okay, relating these two quantities. Criterion. Okay. What's the criterion? What is the criterion? This is the question we are trying to answer. So at first, the criterion was past input energy versus the output future energy. This was balanced truncation, okay, with error bounds and all that. However, balanced truncation, because you need to solve Lyapunov equations, and you saw even in your lab assignments that solving Lyapunov equations is not an easy task. Okay, it's not an easy job. We are trying to do it differently. Moment matching. Moment matching is a direct relation between Y and eta. Relation. We didn't have it here. We had no such thing over here. We are going to impose this a specific condition on Y and eta, and we get the so-called moment matching techniques. The nice thing about moment matching techniques is that they are in a one-to-one relation with V and W transposed. Krylov projections, they are called. You saw last time what a Krylov projection is. Krylov projections, okay? Krylov projections related to R, the controllability matrix, or related to Q, the observability matrix, as we'll see. Okay? And you get a nice class of very nice methods. Okay? Of very nice methods. Of course, the V and W are using the Arnoldi and the Lanczos procedures because they're quite efficient. They're using them, or we are using those. We are building these projections in such a way so we can use the Arnoldi and the Lanczos methods for model order reduction, because those are very efficient methods. There is a lot of information about that in chapter 10 of this book and other books, which I kindly invite you to consult for further reading. Okay? So you'll have to, you don't just need to leave those books lurking around on Moodle. You just need to get your hands on those books, open them, read, and get some knowledge, grab the knowledge from those books and understand these things. Okay? So we are trying to use these projections to do model reduction. Question is how to build W and V. Okay, I said here they are related to Krylov. Okay, now the question is how. How do I get V and W? First of all, we need to understand the notion of moments. Okay, so here they show you how you build V and W. Arnoldi is V transpose V, so V is a matrix such that V transpose V is the identity. Okay, so Arnoldi, W transposed is V transposed. Lanczos, W transposed is different, is other. Okay. Now these matrices, they can be built via moment matching. Okay, so in case the system is determined of state space data, the partial realization problem can be solved in an efficient way. So note that these moment matching methods, they are also suitable or extremely suitable to the case of data-based modeling. Data-based modeling, because you can solve the realization problem, meaning the Markov problem, okay? Constructing the Markov problem, the Markov parameters from data. Okay, so Lanczos and Arnoldi methods, as you can see here. The k-step Arnoldi iteration applied to any pair AB, so to the first equation, x dot is ax plus bu, produces a matrix with orthonormal columns. So that's why V transpose V is the identity, because the columns of V are orthonormal. Okay, so that means that Vi is perpendicular on Vj. That means that the angle between Vi and Vj is half pi, is 90 degrees. Okay, this is, okay, so this means, no, that's the angle, sorry. No, angle. Okay, so this is equivalent to the fact that the scalar product between Vi and Vj is 0. Okay. On the other hand, Vi, okay, this is constant. Okay, and usually any vector V, that's why it's called orthonormal. Vi is actually Vi on Vi scalar product with Vi. Okay, this is usually a norm, if you remember from the second year. So it's something like this. Okay. All right. So that's what the columns of are. Okay, and the reduced order model is this one, applying this Galerkin type projection. Okay, pi, and this is the reduced order model. Okay, so and the main property is that such a system achieves matching of the Markov parameters. Okay, of the Markov parameters. This is quite interesting. Okay, as you can see here. So any matrix, okay, you take Arnoldi operation based on an Arnoldi type of scheme, you get this. Okay. Similarly, you can apply the two-sided Lanczos procedure. Okay, with two starting vectors, namely you start from B and C star or C transpose, and you iteratively produce the matrices Vk and Wk with k columns each. They are not orthonormal, they are biorthonormal in the sense that W transpose V is the identity. And you apply this Galerkin projection again, and you can get another type of reduced order model based on the Lanczos iteration. And again, this time, if you look closely, you match twice the size of, you match a number of moments, okay, or you match a number of Markov parameters twice the size of the reduced order model. So this is more accurate. So with the Arnoldi, it's very simple, but with Lanczos, you can get more accurate results, okay? Okay. They say here that you can look at this Lanczos and Arnoldi thing as a building canonical matrices ABC. Okay, and here there are some interesting details which I'm not going to get into. Okay, now let's take a closer look to the notion of moment. We discussed last time the notion of moment is a time domain quantity. What's very nice about it is that the time domain notion is in the frequency domain, is it's the coefficients, they represent the moments in time domain. Actually, in frequency domain, so if you take the Laplace of this guy, represents the coefficients of the Laurent series expansion around some point. So essentially, if you get a transfer function Ks is Csi minus A inverse B, okay? So this, because it's analytic, because its number of singularities is you can count, is countable, because the singularities are in a countable set, okay, numerabil, they're in a countable set. Then it's analytic in C++, okay. This is from complex analysis, analytic in C++, okay. So you can write this as K around some point S0 complex, okay, S0 is in C minus the eigenvalues of A. Makes sense, okay? So this is Ks0 plus K prime S0 S minus S0 plus half half K S0 S minus S0 squared, and so on and so forth. Okay? So, and these coefficients are actually the moments of your system. Okay? We had this discussion, moments at 0, then you get Padet approximation, moments at any finite point S0 complex, those are rational, that's called rational interpolation. And if S0 is infinity, then you get the realization problem and you get the Markov parameters, okay? And they show you here, this is much more clear. Relation 11.5 clearly shows you the Laurent series expansion. This is at any point S0, then you get the Laurent series expansion at around infinity, okay? These, and you realize, if you remember from chapter 2 or 3, you get the Markov parameters in this form over here, okay? And now let's see what an approximation through moment matching is. Okay, given some system sigma, okay, you expand the transfer function around any point S0, and the moments around S0 are eta j, okay? Then you'd like to find f, g, or here it's a hat, b hat, c hat, and d. D hat is always D, such that H hat has this Laurent series expansion, and this is the moment matching constraint or condition. This is the moment matching condition, okay? This is the moment matching condition, okay? Of course, if you get this around infinity, you get the realization problem of Markov parameters, or it's called partial realization. If it's at 0, it's known as PADE, and it's in the general case, it's known as rational interpolation. Why is it called rational interpolation? Because your original data, let's take at some point k is 0, k prime is 0, and so on, k differentiated n times around is 0. This is the data. This is the data, okay? And then you'd like to build kg of s, okay, to have the same data up to a certain point, okay? Let's say dimension ni. This is where you cut, okay? So you want to have this ks0. You'd like to have this ks0 plus k prime s0, s minus s0, and so on. But note that ks is rational. You can write it like this, okay, where ps is the characteristic polynomial of the matrix A. So P is this guy, okay, and RS is a polynomial with matrix coefficients. The same, KGS, it's also a rational function. So you know that the shape of this is fixed, okay? So this is, okay, where PGS, P index GS, is the polynomial characteristic of F in S. So this is determinant of Si minus F. But note that F and G and H are not known. But that's why it's called rational interpolation, because you want to interpolate this data with a rational function, knowing that the function that generates the data is also a rational function, okay? All right. Consider the system where A is stable and the eigenvalue of the largest modulus is lambda. So this is the largest eigenvalue. The Markov parameters grow as lambda to the power k. The Markov parameters of the system grow as lambda k. Okay, this is not a finished sentence. Probably grows. Okay. To compute the moments, this is the idea, to differentiate every time and compute the moments. That's what they are trying to tell you. This is very complicated and problematic, okay? So you want the following properties of your reduction procedure. Moment matching is achieved without the explicit computation of the moments, and you'll see that the moments are actually in the matrix CV. So this is without computation. This is a bit far-fetched, if you ask me, because essentially when you compute using Krylov projections, you mask the computation of matrices in the Krylov projection of V. So it's actually, this is not completely true. It's not exactly without the computation of the moments, but never mind. I would say with an efficient computation, or using or based on some efficient computation of the moments, okay? And of course, with the numerical analysis, numerical algorithm, people would like to have an iterative algorithm because those are the most popular and the most efficient numerical algorithms. Now, it's telling you they are also known as rational Krylov methods. Okay. Now, they are telling you how to build those projections. And we start with the two-sided Lanczos procedure versus moment matching. Okay. All right. So given a scalar system A, B, this is scalar in the sense that we look first at the seesaw case, single input, single output case, and then, of course, the results can easily be extended to the multiple input, multiple output case. You'll see how. Okay, so given the scalar system, okay, so that's why it's scalar. Okay, scalar because of A, B, C transposed. Okay, single input, single output. Then you get a transfer function K S is C transposed Si minus A inverse B. Okay, and K is defined on C and takes the values or has the image also in C. And note that it's also symmetric. So the single input, single output system is also symmetric because this is a scalar function. Okay, a scalar function. And this is such cases are good to start with. Okay, these are good to start with. All right. Okay. All right. Now, the goal is they say here, they would like to find sigma hat or sigma index G, how we called it, of dimension k smaller than n, such that the first note 2k Markov parameters, okay, so sigma hat is of dimension k, and we want to match 2k Markov parameters, so twice the dimension of the system. Okay, these are the Markov parameters. So we'd like to have this relation 11.7 satisfied, okay, for index I going from 1 up to 2k. How do you do that? You build the k step, you remember from chapter 2 or 3, no, chapter 3, you remember we had the controllability and observability matrices in a limited number of steps. So we compute the observability matrix in k steps and the controllability matrix in k steps, like this. O and R, K. Then you get the k by k Hankel matrix, okay? And you also get, you can also build a shifted Hankel matrix. Note that the Hankel matrix, we remember that also from chapter 3, the Hankel matrix in k steps, which is a truncation of the infinite dimensional Hankel matrix operator. Okay, so this is just a truncation up to step k. Okay, and you also get the shifted Hankel matrix like this. Okay, he says here next we get the key assumption of this procedure, namely that these matrices from 1 up to k are invertible. Now this is difficult a bit because we have to make this. This is not, it looks like a strong assumption. However, in most cases, this assumption is true. In this case, you can compute the LU factorized decomposition of the Hankel matrix in k steps like this. Okay. And you also make another constraint, you impose another constraint on the factors L and U. L is lower triangular and U is upper triangular. This is the LU decomposition. You remember that from the second year numerical methods class. And you define these maps, PL and PU. Note that PL and PU are satisfying this constraint. PL times PU are the identity. Hence, pi is pi U times pi L, so vice versa. This is an oblique projection, of course. And then you apply what I showed you with W and V. And this is your reduced order model. And the sigma hat defined by relation 11.8 satisfies equality, the moment matching equality 11.7, moment matching with respect to the Markov parameters of the system. Okay. Furthermore, A tilde is tridiagonal. This is very interesting. And B tilde and C tilde are multiples of the unit vector. So this is a very specific form of reduced order models. And here is a proof which we are going to skip. Okay, and you also have a corollary. Okay, so the maps pi L and pi U defined are equal to W K star and VK of the two-sided Lanczos procedure. Okay, and we had that defined previously. quite a lot, okay, in the previous chapter. And the Lanczos procedure, of course, also gives you a three-diagonal result, okay? So these are very specific constructions of the reduced order model, okay? Note that you'll see later on that these procedures can be generalized, okay? You need not have only this. So this is about Markov parameter, building this. So this construction, this is not unique. That's what I'm trying to tell you. So this construction is not unique. You can build other O and R depending on the problem. Okay, so this was for the specific case of the Markov parameters. Okay, this O and this R need not have that necessarily. Okay, now let's check the same version of the problem with the Markov parameters, this time in the Arnoldi framework. Okay. Okay, you can factorize in the QR factorization of the K matrix of the controllability matrix in K steps. Okay, and you can build an orthogonal projection pi like this, V star. Okay, V star is V transposed and conjugated. That's why they call it star, because you can have Hermitian matrices since you may deal with complex valued numbers. Okay, and you build since RK is you can get that RK is V times U, then V, if you want to build V, is RK U inverse. Okay, and you know that V star V, okay, V star V is U star inverse RK star RKU. No, U inverse. All right. Now we should get that V star where V star V is U and U is upper triangular. U is upper triangular. Now this should be the identity. This should be the identity. This RK probably comes from the construction of the RK. Ah, yeah, because RK is VU in its term. Okay, is VU. So this is U star V star VU. So this is identity. Okay, this is identity. No, sorry. U. Okay. What am I doing here? U star. No, this is U inverse, not U star here. This is U inverse, U minus 1. Okay. All right. And we are now ready to define, this is the reduced order model. And you get here the reduced order model, since V star V is the identity, like in this relation. Okay. Now, the nice result is that this system, defined with these matrices, achieves Markov parameter matching in the sense of relation 11 point, I think it's 4. 11 point, not 4. 11.7, in the sense of 11.7, okay? But only from 1 to K this time. And furthermore, A hat is in the Hessenberg, is in the Hessenberg form, okay? There is a discussion, of course, that you can get an error expression for the Lanczos model order reduction procedure in the sense that you can compute the 2 norm of the approximation error system. Okay. And They say that this expression essentially points to the rule of thumb, they call here, for choosing interpolation points for model reduction. And this is a way to choose your interpolation point, so a way to choose your S0. Your S0 should be minus lambda 0. So it should be minus the eigenvalue of the reduced order model. Of course, the question is, someone immediately asks, okay, but this is ridiculous because I do not know the eigenvalue of my soon-to-be reduced order model. Of course, you cannot, but you can design an iterative procedure initializing S0 anywhere, and then step by step, you go every time and you choose as the new interpolation points. Okay, so what you do, you initialize without the hyphen, initialize, okay, S0 anywhere, okay, then you get your reduced order model sigma g depending on S0. This one gets lambda 0 as an eigenvalue, okay? Then the new S0, okay, so S1 is the previous lambda 0, okay? Okay, and then the new sigma g of S1 produces lambda 1, and the criterion is decrease of the 2 norm of the error. You check the error every time, and if the error decreases, okay, and you stop down to a certain tolerance. So this is a numerical algorithm based on such line of thinking. Is it kind of clear how you build this? I don't think it's very difficult to understand at this point, okay? We've got specific properties of the Krylov methods. The number of operations needed to compute the reduced system order k and OK. So you can see that you get OKN squared for dense system, OK squared n for sparse systems, versus ON3, ON cube operations you need when you do balanced truncation. That makes sense because in balanced truncations you need matrix inversions, you need solving Lyapunov equations, and you need matrix multiplications, matrix multiplication, whereas here you only need matrix vector multiplications because you just construct those matrices and you do much simpler operations. They say here only matrix vector multiplications are required, so no matrix factorizations or inversions are required at this point. There is no need to compute the transformance order model and then truncate, so you don't do that. In balanced truncation, if you remember, you need to compute the balancing transformation first, and that's quite tedious and costly. And then you perform the neglection and the specific truncation. It's not the case this time. This time we have an iterative procedure here. It just goes along. Okay. They can also be applied to multiple input, multiple output systems. There is efficient way. You change the problem a little bit. Okay. I'll explain up to a certain, if I have time, to talk about the multiple input, multiple output case. Okay. If not, for MIMO, you can look up tangential. In the MIMO case, you can look up the new problem of tangential interpolation. Tangential interpolation. Okay. Okay. Need I remind you what interpolation is? Interpolation is given a set of data. Given a set of data. VI, WI. Okay, so this is input data, and this is measured data. Okay. Find f defined on the space v to the space w. Let's call them calligraphic v and calligraphic w. Okay, such that what wi is f vi. This is the general problem, the mathematical problem of interpolation. You have to understand that essentially control is an interpolation problem, because you want to design a controller such that the closed loop system achieves a specific behavior. The specific behavior is given through data and constraints on the data. Okay? Reference, tracking, disturbance, rejection, all these things, they're all based on interpolation problems. If you carefully remember the Euler parametrization you used to study in the second year in the signals and systems course, in the first semester of the second year, you remember that when you were supposed to design a controller tracking specific reference or rejecting a given disturbance, you used to solve a set of interpolation conditions. So control is also an interpolation problem. Steady state is an interpolation problem. Everything in control and systems in control, every design, less analysis, but most of the design procedures in control, they're all based on solving a specific interpolation problem. This is no novelty, essentially. This is what goes back in the background, in the mathematical background. Everybody knows that. So all the methods you're learning in the other classes, advanced control, okay, or you used to learn in B1, robust control, or optimal control. Essentially, in the end, they're all interpolating specific data you impose from the very beginning. Analytic data or measured data, okay? Practical measured data, okay? But we'll see that in particular, these moment matching techniques are very closely related to this notion of interpolation because they stem as the solution, or they are created as the solution of some interpolation problem we specifically designed from the very beginning, okay? Right. So here you get tangential interpolation. You can look it up in papers if we don't have time to mention it. Krylov methods have simple derivation and algorithms, which is true, when used for eigenvalue estimation, high convergence rate, and so on. However, these methods also exhibit a number of drawbacks, okay? Okay, look, I suggest we have a short break now, and we get back here in 5 minutes. Agreed? I'd like to have a sip of water, please. Okay?
Yeah.
Okay,
Yeah.
fine. I'll see you in 5 minutes, okay? I'm back. Okay, are you people back?
I'm here.
Oh, you're still here. Thank you. All right. Yeah. Okay, so this is the non-disturb. Okay, fine. All right. So, of course, like any technique regarding the solution of any problem we solve as engineers, as scientists, or anything else, there's a number of advantages and a number of drawbacks. So now we're good to go and discuss the drawbacks of these Krylov methods. Okay. Um, okay, there is some numerical issues. I'm not going to get into many details about this. How the most important drawbacks are first of all is this one, that the reduced order model may lose stability, may not preserve the stability of the original model, whereas balanced truncation could do that, if you remember. But we shouldn't be so upset about this issue, because I'm going to show you a more recent approach to this problem of moment matching, a very nice recent approach I've been working on for the past 5 or 6 years. No, actually it's more, for the past, no, I'm sorry, for the past 10 years actually. I've been working on this procedure, and I can tell you we can easily overcome this drawback of stability, because we can impose stability on the reduced order model. Okay, but per se, this is the reality. Moment matching methods, neither Krylov nor the Arnoldi can preserve stability. However, stability, you have another degree of freedom left, the choice of interpolation points. So that means that if you choose the interpolation points in a specific manner properly, you may enforce, or you may regain the stability of the reduced order model. Okay? Okay. There is also a numerical remedy called implicit restart of the Lanczos and the Arnoldi procedures, but this is also numerical. I'm going to show you something a bit different a bit later. The Lanczos method breaks down if the Hankel matrix in specific or in 1 to k steps becomes non-singular. Okay, but this is also not so crucial, I would say, not so critical. What they say here, this is important. The resulting reduced order system tends to approximate the high frequency poles of the original systems. Hence, the steady state error may be significant. Okay. However, you'll see that since they are interpolation problem, we'll notice and will clearly state that these methods or these resulting models will be able, at least with rational interpolation, will be able to preserve the steady state response of specific signal inputs dictated or indicated by the interpolation points we choose. Okay, you'll see at the given point, you'll see that all this discussion, which looks so complicated now, it's going to be significantly simplified by the system theoretic approach. Okay, all right. Well, there is a remark here about the stability and the instability. There is here another example. Here is an example about specific scalar transfer functions, okay, and some specific realizations you might build using these these Krylov projections, we'll pass on further to the discussion about the partial realization problem and in relation to the interpolation. Okay. So Krylov methods achieve model reduction by moment matching, which leads to realization and interpolation problems. This is true. Okay. So now we are going to revisit the partial realization problem of a given transfer function. You remember we discussed that in chapter 4 or 5, I can't remember exactly. We discussed specifically the realization problem of a transfer function. Okay, so suppose we have a system sigma given by ABC. Okay, okay, this is also still a seesaw system. We wish to find the lower dimensional system sigma hat, okay, such that sigma hat preserves specific properties of the original system, okay, stability, norm boundedness, etc., etc. And we'd like to build our system. I showed you how many times, but now we specifically impose this in condition 1.8. We want the reduced order model to be realized in this form, based on the projections W, V, and W. How do we do that? If you build the projections V like this, note that V is the controllability matrix in K steps, and W taken any left inverse of V, then sigma hat defines a partial realization of the system sigma and matches K Markov parameters. Okay. You need not necessarily use matrix V, but you can use any other matrix that spans the columns of V. Okay, so you can use the controllability, the columns of the controllability matrix as basis for a for a space, okay, to construct any matrix V from that space spanned by the columns of the controllability matrix. In general, but note this, this is very interesting, you see, because they say here V is fixed, okay, V is fixed by the columns, okay, the columns of R, and W transpose V is identity, W any, okay, because this is not unique. W is not unique, okay, keep in mind that. W satisfying this is not unique because like I said, V is like this, W transposed, okay, is like this, okay, and this is not unique, and this needs to give you the identity, okay, the identity dimension ni times ni. This is not unique, okay, so you can say that this system psi dot is W transposed A V psi plus W transposed BU and Y or eta. Eta is CV psi, you see, CV psi, okay? This is parametrized. This is parametrized in W because it says here W any. So this is parametrized in W. So this is not only a system, but this is a class of systems. This is a class of systems. However, this parametrization is not easy. Okay, not easy. This is not an easy parametrization, so you cannot easily find W, for instance, such that this system is stable. Okay. Example, how to find W, how to find W such that W transposed AV is in C minus, or even better, such that W sigma of W transposed AV is a prescribed set lambda 0 included in C minus. How do you do that? Difficult. Difficult. So we probably might need other tools. Okay, we might need other tools. Okay. Furthermore, note that sigma hat defined by the 1.8 interpolates the transfer function, the given transfer function of the original system sigma at all points Sj. But who is Sj actually? Oh, sorry, this is different. Okay. Okay, now suppose we have, so this is about Markov parameters. Suppose now that we have distinct points Sj in the complex plane. However, this is not properly, because they should say here C minus the spectrum of A. Now we can define V in this form. Look at this specific form. This is called the generalized reachability matrix. I would say directly this is a Krylov projection. I don't like to use this the notion of controllability and observability for such systems. Okay. All right. Oh, I have here an email with the exam dates. Thank you. Right. Where was I? Yeah. So you see here, okay? So, and just like before, let W be any left inverse of V, okay? So W transpose V is the identity for all the W's possible. Okay, not unique. Not unique. Okay. And then you have this proposition. If you get sigma hat W transpose of sigma hat, okay, I remind you, or let's recall that sigma hat is W transpose AV, W transpose B, CV. Okay, this is sigma hat. So this sigma hat with this V and this W achieves moment matching at the points Sj. Note that these are all zero order moments. Okay, they're all zero order moments. Okay, so zero order moment is C S I minus A inverse B. Okay, so this is the zero moment at points Sj. And this actually occurs. This actually occurs. Okay. Okay. Now, if you have only one point S0 and you compute K moments, you look at all the moments eta 0, eta 1, eta K defined in this S0. Again, you can define V in this form, a Krylov projection, and you can get again any W such that W transpose V is the identity. Then, indeed, all the first K moments. Okay, so here you have eta I S0 equals eta hat I S0 for all I from 0 to K minus 1. Okay, this is what, or here they have J. Well, never mind. Let me write this again. Okay, so eta J 0 S0 equals eta J hat S0 for all J from 0 to K minus 1. So this again happens. So look, specific forms of V and W matrices achieve moment matching. Achieve moment matching. Okay. All right. This has dual forms. So this has a dual form. There is a dual result. You can pick W. You can pick W to be to be what? W transpose actually to be S, let's say S1I minus A minus 1 or minus star C star, okay, SKI minus A minus star C star, okay, or W transposed B S0I minus A star C star S minus star S0I minus A to the power minus K star C star, okay, and then you have any V such that W transposed or W star V is the identity. And now you get sigma hat parametrized in V. So this is dual. You can also have this based on the observability discussion. You can have the same, okay? Okay. A moment's reflection shows that any V tilde that spans the same column space as V achieves the same objective, of course. So you don't need to have necessarily these specific matrices, but any matrix V or any matrix W whose basis is the columns or the lines of the controllability and the observability matrix respectively. So you can do that as well. You can do that as well. But you can also imply both projections. You can have both V, oh, sorry. So no, this is when it's transposed. Shit. No, so I made a mistake here. I'm sorry. Let me rewrite this. Let me rewrite this. Sorry. Like this. Okay. And here, like this. Made a mistake. Okay. So now how about employing both projections? What about that? So two-sided projections this time. This time we are going to match 2K moments, okay? The results just discussed strengthen if the row span of the left matrix W star is chosen to match the row span of an observability or generalized observability matrix. Okay, so what I just showed you, dual, okay? In such case, twice as many moments can be matched with a reduced order of the same dimension as in the previous section. However, this is not always possible. Certain non-singularity conditions have to be satisfied. So we have an additional assumption. We've got an additional assumption this time. Okay. All right. So this is about the case about Markov parameters, but you can also have the general case. So this time you have 2K distinct points, S1 up to S2K. Okay. And you can get the following generalized matrices W tilde and V tilde. Now this time you have to assume W tilde transpose V transposed invertible. This is not very restrictive. Why is it not restrictive? Can you tell me? Note that W tilde and V tilde are matrices constructed by ourselves. So is this restrictive or not? Restrictive or not?
No.
Why?
If we can't make that inverse matrix, we can choose other W and V.
How can we choose other W and V? So essentially we choose different
with random data.
Yeah, not necessarily. We choose other points. That's what you wanted to say. You choose other SIs. You choose other points SI. So if your choice of SI doesn't meet the requirements of this, not restrictive, okay? Restrictive. If by bad chance, if, or not bad, unfortunate, if by an unfortunate chance W transpose V not invertible, then choose other points as I. That's the quickest remedy of this. Okay? So the proposition is like this. Assuming that this matrix is invertible, the transfer function of the projected sigma hat with V equal V tilde and W having this form, note that W hat and V hat with this construction, let's call this let's call this square. So W hat and V hat constructed with square do not make projection like this, okay? But, or however, V like this and W being W transpose V, okay, like this, okay, make projection, since W transpose V is, look at W, okay, look at W, sorry, this is inverse here, okay, so this is W tilde V tilde inverse transposed, W transposed V, okay, it's correct, huh? I think here should be a transpose somewhere. Oh, it's V. It's V star W. Sorry. It's V star W. So it's V tilde transpose W. Okay. V like this. Okay. Okay. So this is like this. This is the identity. So this time, this is a projection. This is a projection. So W and V form projection. Okay. And indeed, if you apply this W and this V, you match 2K interpolation points. Okay. There is a remark here telling you that you can also extend this relation to differential algebraic systems. Okay. So generic systems, these are called descriptor systems with E not necessarily invertible. So you can also extend this to other cases, actually. Okay. And also, you can look at the MIMO case by means of tangential interpolation. You also have here a reference to that in the book, a reference to that. Okay. Furthermore, note that you can easily notice that these projections, okay, for instance, V is this Si, S0, S1, S0, whatever, S1, I minus A inverse B, S K I minus A inverse B. This is the solution, the unique solution actually, and I'll show you why unique immediately. This is the unique solution of the Sylvester equation, AV plus BL equals VS, where S is the diagonal matrix of S1 up to Sk, and L equals 1, 1, 1. It's easy to prove that. It's very easy to prove. Why? Because you just write this. You just write this very easily. We'll discuss this later. Okay? The same W, which is C S1 I minus A inverse C S1 I minus A S1 SK, sorry, I minus A inverse. It's the unique solution of the Sylvester equation Q W equals WA plus RC, where Q is diagonal of S1 up to Sk. This is a diagonal matrix. And R is the vector 1, 1, 1 of dimension K. Okay? This can be very easily proven because of the specific forms of diagonal matrix. It's not very difficult to prove. You can take it as a homework and you can do it yourselves to prove this. For each column of this matrix, you can easily recover these specific forms. Okay? The same holds for the other projections in a single point. Okay? So the same holds for V and W with elements, no, not elements, sorry, with S0 for K moments. It's the same matrix. You had this discussion in lab 5. You had this an exercise like this in lab 5. Now there is a question here: how general is the model reduction by rational Krylov? The response is that it's quite general. Okay, it's quite general. Of course, you can have here model reduction with all sorts of properties, such as stability preservation, okay, such as passivity preservation. This is this lemma. This lemma, if the frequencies in the interpolation points, they are chosen such that the stable spectral zeros and the zeros of the spectral factors and so on and so forth, you can impose these specific properties. There is an example here with an RLC circuit. There is an example here of an RLC circuit, okay? When they build these specific projections, you have this second order model, which is actually passive. Okay, so you can enforce specific properties. This is in a nutshell the discussion about moment matching based model order reduction. In the sequel, we have another view, another approach of the things, using some slides from um, the University of Magdeburg. Peter Benner. Peter Benner is a famous guy in model order reduction, and he had this model reduction course. You can check it out over the internet. And don't forget about the website modelreduction.com. And you get here a different view of things. It starts from the interpolation problem itself. So we had the approach starting from the Arnoldi and the Lanczos methods to compute eigenvalue, eigen and singular values. Now we get the interpolation perspective of things. Okay, and finally, I'll show you the most recent approach of Alessandro Astolfi from Imperial College, my collaborator and my former boss, where we have the system theoretic angle of things. The nice thing is that if these first two approaches, the numerical approach as well as this interpolation approach, if these are quite complicated and quite involved from an algebraic and mathematical point of view, the last one, you'll be very, very surprised to see that only with meager notions from chapters 3 or 2, 3, and 4 from this class, as well as notions you have already found out in the second year, they are actually more than enough to design moment matching ideas. They are all based on signal and system approach. That's why I love this system theoretic approach. And also, the nice result about the final approach is that we get not only one reduced order model, but a class of models, a class of reduced order models. Okay? Okay, let's have a short break, and I'll see you here at 6 o'clock. Okay? To discuss, to partly discuss the slides of Peter Benner. Okay?
Okay.
Okay. Okie dokie. I am back. I am back. Hello.
I'm here too.
Okie dokie. Am stat un pic la televizor, s-a curățat și Dicky Seanu, nu știu dacă ați auzit. Dacă îl știți, actorul. A murit.
Nu știam.
Mă rog, a fost un actor. A fost bunicel, așa, a apărut pe niște filme, fac ăștia acum la televizor, se duce să joace la îngeri, toate tâmpenile astea.
Gata, îl știu. M-am uitat acum.
Da, nu, a fost un actor relativ bun, a fost de top, cum să minte la noi. A fost de top, a fost pe dracu de top. A fost bunicel, da. A jucat pe niște filme de-astea, așa zise, comerciale românești. Mă rog, dacă mă întreb pe mine și alea de 2 lei. Da, să face atâta caz, atâta ne place, bă, să ne umflăm. Nu știu, deci, bă, voi înțelegeți, nu știm să facem, să batem 2 cuie într-un pod, bă. Bă, 2 cuie într-un pod. Am uitat aseară cu maică mea la nu știu ce post de ăsta cu documentare, să vezi ce au făcut chinezii. Da? Orașul de gheață făcut în 15 zile, bă. Bă, în 15 zile, un oraș de gheață, da? Așa. Și ăștia nu sunt în stare să bată 2 cuie. În schimb, la noi totul e extraordinar. Școala românească e extraordinar, cea mai bună de pe planetă. Și suntem ultimii la toate capitolele. E cea mai bună de pe planetă, ca boul ăla de nenorocitul ăla de țigan, de Doru Viorel Ursu, un jegos ordinar comunist, da? Pe realitatea spunea că marea școală de drept penal după Franța. Noi suntem la toate, bă, pe locul 1, pe locul 2 și când cauți la catastif, suntem ultimii pe toate planurile. Da, asta e viața, asta ne e soarta, bă. Asta ne e soarta de capre răioase, bă. Să știți și voi, să țineți minte. Acolo pe unde poate dă Dumnezeu și plecați, că nu-i de stat aici. Să țineți minte de la mine, aici nu-i de stat încă 100 de ani. Ce 100? Încă 1000 de ani. Asta e. Asta. Noi să fim sănătoși. În sfârșit. Așa. Unde rămăsesem? Deci. I was saying, I'm going to present you some of the slides of Peter Benner, actually, because he's German. When I first met this guy, he was in Chemnitz. Now he's in, I think he's at the Max Planck Institute of Germany. Okay, he's at the Max Planck. But by the way, where would you situate the Max Planck Institute and our university? Would you say our university is the second after Germany or the second after the second? Jesus Christ. Anyway, and I'm going to present some of his. He has a lecture. He has a course on model order reduction. I think it's also a master's course. If it's not master's, oh no, it's not a master's course. It's actually a PhD course. It's a bit more advanced. But I think at this point it's good to have a look over these slides and get the hang of the ideas of model reduction from the perspective of the interpolation problem. Okay. Okay. So what's AWE? Because I remembered. Oh, explicit. No. AWE. But AWE. What do they mean by AWE? And never mind. Okay. So the motivation about these methods. Asymptotic waveform evaluation method. Okay, so this is interpolation. That's what AWE stands for. Asymptotic waveform evaluation. Okay, so we've got this original large-scale system. Large scale, I think, is a bit of a far-fetched term. How would you define large scale? Would you say a system of 1,000 states is large scale or small scale? I would say is nothing. Essentially, it's just a system. Large scale, in my perspective, is, for instance, an infinite dimensional system coming from a partial differential equation, such as for instance, the telegrapher's equation, okay? The telegrapher's equation, sorry, or the heat equation, or the ball or the beam equation, and so on and so forth. These equations may define a large-scale system. You cannot call a system of 10,000 or even 1 million ordinary differential equation a large-scale system. But okay, these are philosophical discussions. We are not very much interested in it. However, it's good to have a nice perspective of things and put the things in order. Okay, we do model reduction, but we do not necessarily talk about large-scale systems. Okay, I admit a discretized PDE creates a dynamical ordinary differential equation of dimension over millions. Okay, over millions. Okay, all right, but that's not large scale. Once again, large scale, in my perspective, is something a bit different. So assume you've got this differential algebraic. They go to this general form of differential algebraic equations. You haven't studied in the undergrad or during the undergrad period differential algebraic systems. However, they're present everywhere. Differential algebraic means that it's defined by a set of differential equations as well as a set of algebraic equations, but they can all be caught under this matrix equation E, which may not necessarily be invertible. Here we still have eigenvalues, but you do not have the eigenvalues of a matrix, but you do have the eigenvalues of a matrix pencil, it's called. Okay? And the transfer function is the same, because once you apply the Laplace transformation on this equation, you end up with this transfer function. Okay, and of course you'd like to approximate, because E and A are large matrices, because the state X is a large vector. You'd like to approximate this with a lower dimensional system. How do you usually do this? That's the question. We haven't talked much about it. At first, people used to approximate things using the so-called Padé approximation. Padé was a mathematician. Okay, the Padé approximation approximates any analytic function f of x by a rational function. Okay, by a rational function. And one example, one very strong example I might show you about Padé approximation is e to the power s. This is a function of s, okay, in the frequency domain. However, this is not a rational function. This is an irrational function, essentially. Okay, or it can be e to the power minus s. The problem with this, for instance, e to the power minus s, is that it has an infinity of poles this time. So this is not finite dimensional. However, I'd like to approximate it. Hence, you can approximate e to the power minus s. You can do Euler approximation, so you can do Taylor series expansion essentially, or you can do rational approximation. So you can have 1 minus s over 1 plus s. This is e to the power s. This is a first order rational approximation. You have seen this before. When you do discretization of a continuous time linear system, okay, or a continuous time transfer function, you can use such kind of transformations. Okay, this is a specific. This also denotes a mathematical specific transformation. Okay, so this is Padé approximations. Okay, a rational function. So a rational function is the quotient of two polynomials of degrees n and m respectively. Okay, and the question is, can you approximate the transfer function by a Padé approximation? Okay, we start from rational functions as it is, because we talk about linear systems. Can we do approximation of this? Here you've got Pn and Qm polynomials. Okay, note that the first term Q0 is 1 in the second polynomial, and this is without loss of generality. This is without loss of generality. Okay? And they say here, since Rmn is not changed when both Pn and Qm are divided by the same constant. Okay, and you can write this approximation, this rational function to approximate your given function. How do you build a Padé approximation? Okay, so this, you can add this Padé approximation as a new method of approximating dynamical systems characterized by rational transfer functions. So, Padé approximation, you build these two polynomials, Pn and Qm. The coefficients of Pn and Qm, how do you compute the coefficients? This is the important thing. Okay, you require that fx and Rnmx agree at x equal to 0 and their derivatives up to n plus m degree at x equal to 0. So you have a Maclaurin expansion, okay? You've got the Rnm, and this gets you the fact that Rnm minus f is e of x, which can be written in this form. Later on, Rnm minus f is Pn divided by Qm, because that's how you build Rnm at first, minus f. And you apply the polynomial identity. Two polynomials are equal, hence their coefficients are equal. And then you get a system of m equations and m unknowns, okay, in the coefficients of the Rm and Rn. Okay, so this is up to order n, and then you can continue this up to order n plus m, because you have also the m coefficients of the denominator. Okay, so you complete your n system up to m plus m. So you have m unknowns and m equations in 2. Qi's can be obtained solving 2. And pi's follow immediately without solving the equation. So essentially, you can split this system in 2 parts. This one you solve, and this one you just build based on the solution of 2. Okay, based on the solution of 2. Example, you have a very nice example here, which you can follow. You have this function fx, which is square root of x plus 1, with x between 0 and 1. Okay, and you get f0 is, you compute the first coefficients of the Laurent series expansion, okay, or Taylor series expansion, whichever you prefer. Okay, this one. Okay, so this one you compute because this is the data. This is the data from f. This is the data from f. Okay, all right. So it's easy to compute these coefficients because you get the data from the function. You do the Taylor series expansion and that's it. Okay, and you build the approximation based on made of, or the rational approximation of order 1. So both polynomials, the numerator and the denominator, they both hold degree 1. Okay, and this is the approximation of degree, where this is the strictly proper approximation with the numerator of degree 1 and the denominator in degree 2. And this is how you compute your coefficients. Okay, you see here the systems. Okay, note that these systems are linear systems, so they are linear algebraic systems. So to build a Padé approximation, you need to compute to solve linear systems. This is not so difficult. Hence, it only shows you that the Padé approximation is rather a numerically efficient tool. Okay, it shows here you've got the graphs. Okay, Padé approximation, however, look, is accurate essentially around 0. Also, you can easily notice that the Padé approximation is more accurate. Okay, Padé approximation is more accurate when n and m are large. When n and m are large, this is not good. So essentially, the error, the approximation error, is somewhat proportional, okay, to the degrees of the polynomials that make up the rational approximation. This is not nice, because you need very high degrees to get very accurate approximations. And that's something we really do not like, because we start from rational functions of large degrees. So if we start from rational functions of large degrees, we'd like to construct rational functions of low degrees. Okay? Okay. Now, what is this waveform, asymptotic waveform expansion method? This is a method trying to find the Padé approximation h hat of a transfer function h of s. This is what they try to do. Okay? So, first of all, what's the degrees of n and m to choose? Okay, we want to use the Padé approximation R, depending on degrees n and m. How do you pick them? How do you pick them? And there is a result here, given in this proposition. For a fixed value of n plus m, the error is the smallest when Pn and Qm have the same degree. So essentially, you'd like to have degree n equal to m, which is not very nice, because then you might have zeros at infinity. And you do not like that, because maybe your original system did not exhibit such property. So you cannot add properties that your original system did not have. Well, maybe this is the least of your troubles in this case. Okay, or you can have a remedy about that. Pn you can be taken with 1 degree lower than Qm. But then there is another issue. The more interesting issue is that if your original system did not exhibit any zeros, how come your approximation exhibits additional zeros? Okay, and here it's shown how to get the Padé approximation. You have a system. Okay, note that the Padé approximation is also in a one-to-one relation with moment matching at 0. And maybe it would be nice of you to prove that. Okay, even on specific examples. Okay, so I think it's also this proof is also caught in this framework. So given a dynamical system of this form, okay, you get this transfer. You can write the transfer function in this form, provided A is invertible, and to get the rational approximation, the Padé approximation, you have to do this procedure. And look that you get, you can write your h of s in this form. This is a residue form. Okay, the numerator is a polynomial of degree mostly n minus 1, and denominator is of degree n. So it's natural to take m equal r and n equal r minus 1, because this is what happens when you do this. So note that this h is identical to this h. There is no difference between them. So this is not an approximation, but based on this form, based on this residue form, we are going to build the Padé approximation of this system. You pick m equal to r, n equal to r minus 1, and this means you can build this function in this form. in this form. Okay. What are the requirements to be able to apply a Padé approximation? You have to have the same, you see, the values at s equal to 0 and the derivative of s of hs equal to 0 should be the same. So this is moment matching at 0. It's actually proven. So essentially, okay, Padé is identical to moment matching, so it's here. You don't need to prove anything. At 0, this is moment matching in 0. This is moment matching in 0. Okay? And this is how you build it. You have the derivatives at 0, the coefficients are all, so on and so forth. These are the moments at 0. Moments of the transfer function at 0. These are the moments of the transfer function at 0. Okay? You can easily write your transfer. This is the series expansion. This is the series expansion. Okay? Series expansion at 0. This is the series expansion at 0. Okay? And this is the series expansion at 0 of h tilde. And you nicely do the polynomial equality. This ends up with two systems of linear equations in the coefficients. You end up with two systems of linear equations in the coefficients. Okay? And finally, you solve these two systems and you get your approximation. You get your approximation. Okay? However, this may not be accurate due to some issues at high frequency, especially. So for high numbers, for high frequencies of S, this is not possible. Okay? This is partial here, not parial. It's just a typo. And the remedy for this is to consider the problem a bit differently. Okay? You do a partial fractions decomposition. You remember that. You used to do that quite a lot in the second year at the Signals and Systems course. You used to do a partial fraction decomposition when you were supposed to compute the response of some linear system at some given input. Okay? This is how you do it. How do you compute the poles and the residues? Kr are called residues. Okay? And k hat are called residues, and a hat are the poles. Okay? Note that a1 hat up to ar hat are nothing but the roots of this polynomial. Okay? Okay? And we know how to compute this. Okay? So we need to compute the residues k1 hat, k hat 1 up to k hat r. And you do this from the Padé approximation, and you get another system. Look here. This is another system of equations in the unknowns k, because you already know the a hats. And note that these are the moments. These are the moments. Okay? So the residues can be easily obtained solving the above equations. Solving the above equations. Once this is computed, you can easily get this canonical form of your reduced order models. Okay? Okay, but this can be done differently. You do not need to write this pole residue form. You cannot do moment matching at 0. Once again, we have to remember that these properties are identical. So let's solve a moment matching problem. How? Truncating the Taylor series or the Maclaurin series expansion up to order, truncating the series expansion at order k. Okay? So the Padé approximant often gives a better approximation of the function than truncating the Taylor series, but it still works if the Taylor series does not converge. I think it's good to do the Taylor series here. Okay? All right. So how do you implement the algorithm? You need to get your QIs, okay, to solving equation number 3. Let's go back. So you need to solve this. Okay? You need to solve this. Then probably you need to solve that. So you compute this polynomial once you have the QIs, and you get the roots A1 up to AR. These are the poles of your system. Then you solve 5 to get the residues, and then you form the transfer function. So they say, or they claim, that this pole residue is much easier. I'm saying that solving the moment matching problem is even easier than this in the system theoretic approach. You'll see. You'll see. Okay. They say that step 2 are implemented in this function. So you can use in MATLAB this specific function. So how do you do this in MATLAB? You solve 3, you get the PIs from 4, you use residue PQ in MATLAB to get the poles and the residues, and then you form the transfer function and you get this. Once again, this is very nice. However, looking at the approximation errors, once you have Padé approximation, even in this form, they are quite large. They're quite large. Okay. How to compute the output response in time domain from HS. Definition of the transfer function. Here it shows you how to compute the output. Okay. Note, now it's easy to compute the output because once you have this form of the reduced order model, these are in time domain. Once you get Laplace inverse of this function, you get these y's. This, do remember here, but that H of S defines linear systems. So once we have linearity, you get the superposition principle. You get the superposition principle. Okay. So you can easily compute your response. Okay. However, this method is numerically unstable, they claim. Because probably you due to the fact that you need to use this inverse, which might cause serious problems. Okay. And it shows you here what numerical instability of this means. Okay. I'm not going to get into these very numerical details. Okay. Angle between two vectors. Okay, so this is something related. You remember I was telling you about the orthogonality of some vectors in the matrix V in the Arnoldi step, where you had Vi perpendicular orthogonal to Vj. Now remember that you have the dot product between two vectors, or the scalar product, which is this one, geometrically. Okay. This is the inner product. Okay. And orthogonality means that you have this angle to be, you would like the cosine of this angle to be 0. So where is the cosine of the angle 0? Unless it's half pi and multiples of half pi. Okay. So that's what orthogonal means. Okay. PB is the projection onto A. CB minus PB is also, of course, a projection is orthogonal to the the difference, the C minus PB, the C is actually orthogonal, look here, is orthogonal to the A. The A is the space where I project B onto. Okay. You should remember this from the signal, from the signal techniques course from the second year. Okay, projection. Okay, and it shows you here, and this M here is given by this formula. Okay, so an important information: the space spanned by B and the vector A is equal to the space spanned by C, which is this difference between the projection and the original the space where you project. Okay, so these spaces are equal. Okay. All right. Okay, here it shows you these are important from for some numerical issues where they show you a Gram-Schmidt process. Okay. All right. And here you can see, if you remember, you can see, just like I showed you in the book of Antulas, the Arnoldi and the Lanczos procedure. Okay. Okay, note that here you have span of V1, V2, VQ is the span of the columns of the controllability matrix in P steps. What's the output of this? The output is a Hessenberg matrix HI for each space VI. Okay. So you have implicit moment matching based on this Arnoldi step. How? It shows you here just what we've discussed many times. X is equal to Vz. Okay, V is the projection. You have the Taylor series expansion. Okay. You define the notion of moments for a single input, single output system. Okay. And you apply the asymptotic waveform expansion method to get the Padet approximation with moments at zero. And here it shows you how you build. Of course, if you want to build, to build a reduced order model that achieves matching of dimension k to achieve matching of k moments at zero, fine. You use the Arnoldi based procedure. Whereas if you'd like to match 2k moments at zero with an approximation of dimension k, you do the Lanczos two-sided procedure. And it shows you here how to build the projections. Okay, the Petrov-Galerkin projections. And here are variants of the same procedure. Okay. You can also do this Padet approximation by applying this. You can apply the same procedure to multiple input, multiple output systems as well. Okay. However, note that moments, if for a scalar transfer function, the moments are for a transfer function, the moments are scalars. For a matrix valued for a transfer matrix, the moments are matrices this time. So you kind of need bigger storage for such systems. Okay. Of course, you can preserve passivity with Padet approximation and so on and so forth. Okay. They say here a single expansion point. So to do moment matching at one point is good for the Padet approximation. However, you can do rational interpolation by matching several moments at more points in at more complex frequencies or points. To do that, you need to solve linear systems. Okay, and here it shows you how you deal with multiple points. And here, step by step, it shows you how to get your Krylov projections. For instance, you need to get a V. Okay, you need to get a V here. All right, such that this relation 12 occurs. Okay, relation 12 is based on the columns of the controllability matrix. The same goes for the W to get the columns or the lines of the observability matrix. Okay, and finally, finally, all right, you can get both projections W and V and build your projections, not the projections, you get the matrices, sorry, W and V, and based on them, or W tilde and V tilde, as Antulas denoted them earlier, and based on them, you can build your projections W and V. Okay, and you get the relation or the theorem. You get your result in this theorem. Okay, Grimme is a PhD student who had his thesis on this subject. So for both single input, single output, and multiple input, multiple output systems, if W and V satisfy relations 12 and 13, then 2p moments can be matched. Okay, this is for a single point. Now, if you have multiple points, you can build the projections W and V satisfying relations 14 and 15. Okay, note that 14 is related to a generalized controllability matrix, and 15 is related to a generalized observability matrix. Okay, but if you build these projections, you can indeed achieve moment matching or double moment matching at multiple points in the complex plane. Okay. Okay. All right. Now you get here. Yeah. How to decide expansion points. This is an important problem. There is no systematic way at this point to select your interpolation points. Essentially, this is a procedure based on trial and error as well as engineering experience. Okay, there isn't much to do. However, people here are trying to give a more systematic way to select expansion points, measuring some norms. I'm not sure how good this is. However, there is an example here on how to decide interpolation points. On the other hand, if you want to minimize the H2 norm of the error, this theorem is crucial, essentially. This is a crucial result. And please keep this in mind, because from this result stems a famous, and one of you will give an exam from this paper, IRCA algorithm, iterative rational Krylov algorithm, stems from such a result. So essentially, this is a necessary condition. So you want to solve. Okay, you can pose. Okay, or we can pose minimizing H2 error norm problem. What is this? What is this problem? So this problem is this. Given Ks as A, B, C, find K hat S given as A hat, or I would say FGH because I like this notation more. FGH, okay? Here A is Rn times N. Here F is R ni times ni. N ni smaller than N. Okay? Such that K hat S solves minimal of all rational functions K hat of the 2 norm error. Okay, solves this problem. Okay, this is the 2 norm. This is the model reduction problem based on minimizing the H2 norm of the error. Okay, so note that this is a non-convex, non-linear, infinite dimensional problem. However, there is a solution. There is a solution based on first order optimality conditions. Okay, you should know this from the optimizations class. Okay, now these necessary conditions yield the following result. If h hat solves this problem, if h hat minimizes this problem, okay, and assuming that h hat has simple poles, but this is not necessary, you can have multiple poles as well, then h hat interpolates both h and its first derivative, at lambda I, okay, at lambda I, where lambda I at minus lambda hat I, where lambda hat I are the poles of the approximant. These are poles you do not know. However, you can build an iterative algorithm, like I showed you earlier, based on this notion. And this iterative algorithm is IRCA. There is a paper you have for the exam, but all of you can read this paper exactly on this subject. Okay? How to decide expansion points locally. Here you have algorithm for both single input and single output system, and this is how this IRCA algorithm looks like. This is an implementation in pseudocode of such an algorithm. And here you have the solution. It's not a very complicated algorithm. It converges. There is discussions. Well, the inventors of this algorithm tell us that this algorithm converges. There is actually recent examples showing us that this is not true any longer. There are cases when this algorithm diverges. Another drawback is that you might not necessarily get stable models, even if you start with a stable model. However, it solves the problem, which is a nonlinear problem, remember that, but it solves the problem in a few steps and with a limited number of operations. This is something like k square n or something like that. On the other hand, from a theoretical point of view, there is a paper by Mehr and Lümberger as in the Lümberger Observer. There is a paper from '67 from the IEEE transactions on automatic control, giving you the frequency conditions that these people used 30 years later to design this IRCA algorithm. Okay, this is very interesting, and I invite you to study this thing and look at these slides. Okay, all right. At this point, I'm going to stop and I'm going to ask you if you have any questions. Questions, please. questions, please. Have you got any questions?
Please. No, I don't know.
Okay. Okay, fine. If no questions, then next time